Good morning all. Welcome to the seminar on quantum cryptography. We are going to start the session. First of all, I would like to have a few words about this seminar. The theme of the seminar is on quantum cryptography. As all of us know, the present century, we are witnessing the applications of quantum concept developed during the past century. One of the prominent applications of quantum concept in the present century is in the field of quantum cryptography. Quantum cryptography, classical cryptography is the art of sharing secret keys or secret information between two parties. This technology is developed based on the mathematical concept, mathematical complexity and computational complexity. These systems are vulnerable to computational power. If the computational power exceeds, these systems can fail. In that scenario, the concept of quantum cryptography is found relevant. In quantum cryptography, we are tapping the concept of quantum mechanics to ensure the security of the key or information. We are using qubits instead of bits in the quantum cryptography protocols. I think in India, only few groups are working in experimental aspects of quantum cryptography. Today, we are organized this seminar. The two resource persons are having experience with more than 10 years. Both of them are having more than 10 years experience with experimental aspects of quantum cryptography. This is a relatively new field. I hope by attending this seminar, you can enrich your knowledge on basic concepts of quantum cryptography as well as some advanced concept and experimental aspects of this quantum cryptography. So with this, I am going to introduce our resource person for the first session, Dr. Rubesh Kumar. He is an experimental physicist at the University of York, UK. He obtained his PhD in discrete variable quantum key distribution. All these terms will, I think he will discuss during his talk. What is quantum key distribution? What is discrete variable quantum key distribution, etc. From University of Camerino, Italy. He is having more than 40 years of research experience in the field of quantum cryptography from elite institutes such as University of Warsaw, Poland, Telecom Paris Tech, France, and University of Cambridge, UK. He is currently involved in the development of systems based on continuous variable quantum key distribution system, and this project is under the Quantum Communication Hub of UK National Quantum Technology Program. Today, he will deliver a session on continuous variable quantum key distribution. I welcome Dr. Rubesh Kumar to handle the session. Thank you.
Thank you, Sachi, for giving an introduction. There you go.
Yeah, please.
Okay. Okay, so before I start, okay, so we're gonna have this problem probably. Yeah, sometimes you cannot hear me, so I'm not going to ask you, can you hear me or not? I'll be back. It's this internet problem if that happens. So I hope everyone can see the screen.
It's okay. Fine.
Okay, so let's talk about this. Is the talk. Okay, so today I'm going to talk about quantum cryptography with the continuous variables. I'm not going to do the most high-level things. So trying to explain things in a more fundamental way, in a simple, orally simplified way. My name is Rupesh Kumar, as Sajeev said. So I'm from Quantum Communications Hub, Department of Physics in the University of York. So before I go to the subject, I have to mention this. In the UK, we have this National Quantum Technology Program. So we have 2 phases for each for 5 years durations. One started from 2014, ended last year, and now we are in the second phase of the hub for the next 5-year program. And in this quantum technology framework in the UK, we have 4 different hubs. For different sectors of the quantum technology. One is the quantum technology hub for sensors, so how to use the quantum technology for sensing and timing. It's led by University of Birmingham. Another one is for imaging, led by the University of Glasgow, and for the quantum computation and simulations and related works, it's Oxford. We to report the people outside the basilica about the selection of both. So this is, you can use SMOC for communication. Radio waves, another one have radios. Radio modulates the signal, the carrier wave, which is a radio wave, with your sound. So that's a modulation. Then you have to demodulate to extract the signal from the carrier wave. We have fiber optics. Yeah, so when we can buy this media converter, plug that into your PC, your LAN cable goes through you can connect this to this media converter, convert the electrical signal into optical signal. So you can buy this module, with quite cheap. It has a laser inside, lasers on and off, so that's your zeros and ones. The receiver is a photodiode, you can buy it. It's the simplest version, you can go to maximum 1G with this small box. The heaviest one is something like this, it is for optical networking. They have more complex modulations. It's not just laser on and off. It's some amplitude and phase modulation, much complex, and then you can build an entire optical network around the world with these kind of boxes. What you are seeing here is an optical network node, which consists of, you can see 4 of them there, which are actually the nodes for a quantum key distribution system that we have built in the UK. So before we distribute these systems around the different places, we set it up in a single room, and then that's why we have this picture here. So it is quite complicated, but when you look at this, it's quite complicated, but when you are trying to understand, it's quite simple and then silly. So the classical communications, we use SMOC, there is light on and off, you can have different colors, you can have different intensity of light, you can have a phase modulation, amplitude modulation. All of these things are distinguishable. You can separate each signal, you can understand what the signal is by just looking at it. So they are distinguishable. So what? So you may ask, so what? What's wrong with that? Yeah, the problem is, so if you transmit this message publicly to your receiver, yeah, they get they understand the meaning of the message, but also whoever gets this message, they can also understand privacy. So how to make it secure? That's the question, how to make the classical communication secure? So the situation is like Alice. So normally we have 2 parties, the transmitter and the receiver. Transmitters we call transmitters Alice, and the receiver is Bob. Alice wants to send some message to Bob. But there is Eve, eavesdropper. Eavesdropper is who come to listen to your transmission, so disturb your transmission. Hackers, government, whoever, your friends, enemy, whatever. They listen the communication. They call eavesdropper. Eavesdropper also gets a copy of the transmitted message. So, what Alice and Bob can do, they can encrypt. Alice can encrypt the message using a key, and then send this encrypted message to Bob, and Bob retrieve the message with the same or different key. Yeah. So you have encryptor. You need encryptor that encrypts the message with a key, then make it. It looks like a meaningless. So there is a text, then it looks scrambled message, scrambled the text, the bits, then sent to Bob. He also gets a part of this message. The encrypted message, but only Bob has the key. So Bob has a decryptor. So Bob decrypt the message using the key and then get the message. So, but to decrypt the encrypted message, you also need a key. Yeah, so that's the thing. So the situation is here. So the first encrypted message, or first crypto systems they used is called SkyTel. SkyTel is actually you can take a cylinder and you can take a string or a tape, leather tape, divide it over the cylinder and write your message in the horizontal way along the direction of the cylinder. That's your message. To read the message, you need the same cylinder. So who used this? Spartans, the ancient Greek. They use this one. They call it SkyTel. So you can try that. You take a pencil and then write this, make a SkyTel and write the message on it, and then that's your secret encryptor and also a decryptor. So here you use this key. Key is the diameter of the cylinder. So there are two main categories. Using the same key, different key for encryption and decryption, this is called asymmetric or public key cryptography, which is not really secure because the assumptions are based on unproven mathematical concepts, could be weakened or suppressed by theoretical or practical advance. For example, the quantum computers. The quantum computer. Right now we have the asymmetric cryptography. The most famous one is called RSA, which is based on factoring prime numbers, and then it is proven that quantum computer can factorize big numbers in polynomial time, so it can weaken the RSA crypto systems. Or a smart guy, a smart mathematician can come up with find a loophole in the structure of this encryptor or decryptor, and then weaken and break the code. So there's some problem with that one. But using the same key for encryption and decryption, quite safe against the theoretical and practical advance. So now the problem is how to distribute the keys, because you need the same key for encryption and decryption. So how to distribute the key? To distribute the key, you need some conditions to satisfy some conditions. One is the carrier of the key should not be copied perfectly. So if you can copy the carrier of the key, you can extract the key from that. So Eve gets so it's like Ali sending the key to Bob on a carrier or somebody. It can be a person, or can be light, or can be electrical signal, can be a letter. And Eve also gets a copy of that, and then they shouldn't copy it from the communication channel. Even if Eve makes a copy, or even if Eve trying to do some measurements, then you get indication from your carrier that there is an eavesdropping activity. How to do it? Okay, let's imagine you have some systems to do it. So Alice sent this key to Bob on a carrier, let's say light, but all of the light doesn't reach to Bob, so there are noise. So the situation is like this. So there are the information sent by Alice and the received by Bob, there is overlap. They are not completely overlap. There is some overlap. That is called the mutual information between Alice and Bob. And also there is some part goes to eavesdropper, and that information gained by Eve. So in a simple sense, we can just do this to make information that's secure against Eve, remove Eve's information from the mutual information, then whatever left there, you convert that into a key. Simple as that. So this is the idea behind all this quantum cryptography, quantum key distribution system. So you make a correlation or correlated data between Alice and Bob, and then remove eavesdropper, and the rest of the things are secure. They call it theoretically secure. Okay, not they. I call it theoretically secure, the community that I work. Because these systems cannot be a physical channel. And we have eavesdropper. So these are the situation, three parties, Alice, Bob, and Eve. Eve has some superpower. She can measure whatever the laws allowed by the physics. So imagine all the laws in the universe, same. Not imagine, it's the same. Yeah, but we don't know what happens inside the black hole. So we are not talking about that one. But here, the measurements are allowed by the laws of physics. And Eve can use quantum memories, so which means Eve can store the quantum state. She can measure it. She can perform some kind of special measurements. Eve can use whatever the resources, money. Eve can buy anything with money, so it can use whatever resources, computation power. She can do whatever. So she is ultimate power. So when you develop a new theory for quantum distribution or find a new protocol, you need to understand Eve has superpower allowed by physics. And what Eve can do here? So Eve can read Alice and modify the explanation. Once we have waves and particles. Light is a wave, light is a particle. So we can have two concepts. One is a Fock state. The Fock state doesn't have a phase information. It's just a kind of a particle thing. But in coherent state, you have phase information more suitable for explaining the light as a wave. So when there is a wave, you have phase and amplitude. So, and also we're going to see a lot of things like indistinguishability in quantum superposition, uncertainty. You cannot copy, no cloning theorems, no Go theorems. So what is this? These things are superposition. Yes, superposition is like take a photon and split it. Yeah. So take a photon, split it, and then you increase the dimensionality of the photons. So you can make a two-dimensional, three-dimensional, higher dimensional by splitting the photon. Or can you do it? Really? Imagine you have a beam splitter. You are sending 100 photons to beam splitter. Beam splitter is 50-50 beam splitter. So it transmits 50% of the photons to port A and 50% of the photons to port B. Yeah, so you get, if you send 100 photons, you get 50 at A and 50 at B, right? What happens if you send one photon? Yeah, so you think, okay, you split the photon. No, you cannot do it. You cannot split the photon. Really, you cannot. Impossibility, because they are fundamental, the minimum quantity. That's why I call it the quanta. So what you have, it's a superposition of photons, like half of the time. The probability, you can find half of the time the photon at port A and half of the time at port B. So we have now made a two-level systems which are in superposition. That is the qubit. So this is called a qubit. So we have a horizontal polarization of. So you have a photon which has a polarization horizontal or vertical. You can combine them to make a 45-degree polarization, and a 45-degree polarization is a superposition vertical. This is a polarization qubit. You can make a qubit with a different two-level systems and combine them, make a superposition. And imagine this. So you have this superposition of one photon in a different levels, and you have another photons, and then you correlate them. So you correlate the superposition of two different photons, and that is called entanglement. Okay, this is not the subject, but okay, I just told that. So we have this discrete variable quantum key distribution, which use qubits, multi-level systems or two-level systems. You can make a discrete variable QKD with a higher level quantum states. But the most famous discrete variable system is this. So imagine here this polarization at 45 and minus 45 degrees. That is one that makes your basis, orthogonal basis. You have another one, horizontal and vertical. And now these two bases are mutually non-orthogonal in sense that you can find a superposition of one in another basis. So Alice makes four different polarization, horizontal, vertical, 45 minus 45, and then you can stream it to Bob. And Bob can measure it. So to measure the horizontal vertical polarization perfectly, you need to know that Bob is measuring with the horizontal vertical basis with a beam splitter, polarization beam splitter, such that the horizontal light passes through and the vertical reflects. Oh, it's a theoretical problem here. I have to change the beam splitter into other way. Okay, and for the 45 and minus 45, you have to first rotate the 45 minus 45 bases into vertical and horizontal with a wave plate. Then you detect the normal beam splitter. So these two different basis measurements allows you to understand which polarization Alice has sent. And if you assign a bit to each of the polarization, then you can transmit a key. Then how you detect if? Okay, imagine Alice prepared the polarization at edge. Polarization. Sorry, Alice prepared the qubit in a horizontal polarization and then sent to Bob. In the middle there is Eve. So Eve thinks, okay, the incoming photon has, she doesn't know what is the polarization of the incoming photon, so Eve has to measure it. So Eve doesn't know which basis. She randomly selects one of the bases, which is 45 and minus 45 bases. And this is a system for measuring the 45 and minus 45 bases. So she has to rotate the polarization to horizontal vertical, then measure it, and then remember, as I said before, the horizontal polarization is superposition of vertical and horizontal. So with half of the time, Eve gets a click on this detector at the 45 degree that I assigned for 45 polarization. Then Eve has to recreate it. So Eve say, okay, this is a 45 degree polarization. She recreates that and then sends it to Bob. Imagine basis at Alice prepare the state, which is horizontal and vertical. Now Bob gets a click at the vertical polarization. So Alice sends the horizontal, but Bob receives the vertical. That's a noise, right? And then here we go. Now Bob gets a click at the vertical polarization. So Alice sends the horizontal, but Bob receives the vertical. That's a noise, right? And then here we go. That you detect the eavesdropper. So whatever the noise at the detection that you assign to eavesdropper, and this is the simplified explanation of discrete variable QKD, and this is a particular protocol called the BB84. It's invented in 84, and then first, hello? Okay, some noise. Somebody, could you please shut down your microphone? Okay, thanks. So this is a discrete variable QKD. Okay, now we are coming to a continuous variable QKD where I use coherent state. The coherent state, okay, so in sense that I'm more, instead of the Fock state concept, the qubit concept, two-level systems, I'm using many levels using a coherent state. So how to make these things the coherent state or continuous systems in continuous variable having superposition or uncertainty, indistinguishability? How we do this? We have a set of states called vacuum state in a phase space. This is called a phase space where you can represent amplitude and phase of the light in an XY axis in Cartesian coordinates. So you can have different states there. You can have a thermal state which has some biggest uncertainty in its amplitude and phase. You have amplitude and phase. And then you can squeeze the uncertainty in one quadrature, one amplitude, and then increase uncertainty in phase. They call it squeezed state. So you have this quantum nature. Who gives this uncertainty? I'll tell that in the next slide. Before that, okay. So imagine we have a laser, and from the laser, there's light comes out of the laser, and it has millions of photons, and they're considered as classical. So you can precisely measure the amplitude and phase of the signal. Since you can measure the amplitude and phase precisely, that means you can transmit a data on it. Because whenever you transmit the data, you need to measure it precisely without any problem. So you have the classical signal here, bright intense laser light. It can precisely give you the amplitude and phase information, and then you can measure this amplitude and phase in terms of quadrature. There is no systems in this world that gives you a amplitude and phase information at once. You have to project. So we are measuring the amplitude and phase of the light in terms of quadrature. So X quadrature is, so imagine amplitude and phase are in polar coordinates, which is a different representation than the Cartesian coordinate, which is XY representation. So you have to project the coherent state onto the x-axis, which then the value is called the X quadrature. You can project the quadrature into the amplitude into the coherent state into P axis or Y axis, called the P quadrature. So you can make amplitude and phase modulation, but you measure them in terms of the quadrature. And the quadratures are measured with respect to a reference signal. So now the axis, the X and the P axis, are in reference to another light, intense light, which is called a local oscillator. So you have two systems. One is your signal, then you have a measurement signal that is called the local oscillator. You mix the data signal with the local oscillator to extract quadrature information. By combining the quadrature information, you can recreate amplitudinal. That is it. To communications, we have different amplitude and phase modulation schemes. So you can transmit a lot in a single pulse. They're generated by, take a laser, amplitude and phase modulated. You have these different structures, formats of the data. Then you mix that with the local oscillator on a beam splitter, and then the output of the beam splitter, you convert that into photocurrents, then subtract it and amplify it, you get this quadrature information, and a combination of that can recreate your transmitted data. But what happens if you attenuate light into near to vacuum? Then you started to see the uncertainties because of Heisenberg uncertainty principle. You cannot precisely measure here X and P quadrature of the coherent state that near to the vacuum. When you go away from the vacuum, this uncertainty is very low compared to the amplitude. So you come near to the vacuum, which means your signal has very few photons, and then you started to see this uncertainty. So you cannot do data because you cannot precisely measure it. The exact value, you cannot precisely measure it. So it is useless to transmit any meaningful data, but it's useful for generating random numbers out of it, which is our key for encryption and decryption. So we are mainly dealing with a protocol called the Gaussian modulated coherent state protocol. You'll see that. For that, we need a signal which shows uncertainty in quadrature values. And we prepare the state, the Gaussian states, with the modulating amplitude and phase. We detect it with the vacuum sensitive detectors, measurements. And then after that, we make a key generation with some procedures called reconciliation or correction and trace amplification. I'm not going to do the deep level of those things, but I'll try to explain. So here is the protocol. It's actually, we have a phase space, and we generate a lot of coherent state near the phase space. So you can imagine each dot is a coherent state, and the size of the dot is actually the vacuum noise on it. And the distribution of the quadrature is Gaussian. That's why the protocol called the Gaussian modulated coherent state protocol. And then he sent this to Bob. So how you detect eavesdropper? Imagine the circle, each red dot is the coherent state with the uncertainty in its amplitude and phase. Eve has to measure the state first, but she cannot precisely measure it because of the noise. Then she has to recreate it. When she recreates, she adds more noise on it. So when Bob measures it, Bob will see an increase in this noise level in his measurement, and that indicates Eve. So it's like not only Eve, Bob, they cannot precisely measure the current incoming coherent state, but whenever they want to recreate it, they add more noise on it, and Bob can detect it. That's a way to detect eavesdropping in CDQKD. So so the system for generating these signals are exactly like the current communication system. You have a laser, you modulate the amplitude and phase of the light, but you need to attenuate it down to a few photons, or you need to vacuum. You also need a copy of this the laser light, the bright light that serves as the local oscillator. So you can transmit the signal and local oscillator to Bob in a different realization of CVQKD. You can generate local oscillator at Bob. But at Bob, as I said before, Bob mixes the local oscillator with the signal on a beam splitter. Bob can modulate the phase of the local oscillator by 90 or 0 or 90 degree, then measure X or P quadrature. Then in the end, Alice and Bob, they must have a correlated data. So if you plot the correlation of the X quadrature sent by Alice and the X quadrature measured by Bob, you get a kind of a graph like this, a figure like this. So this shows there is a correlation between X quadrature sent by Alice and P quadrature sent by, X quadrature received by Bob. You can also do this for the P quadrature as well. So imagine this one. Okay, so you have seen this. So they can estimate, Alice and Bob can compare the quadrature values and estimate the mutual information. And from the noise, they can estimate the eavesdropping information, and then they have a correlated string of analog data. They need to change the analog data because the quadrature value can have any values in the phase space, so you have to convert them into binaries. So you need to map it. So it's actually converting analog data into digital data. So it's called binary mapping. This is a very old concept. The new concept is quite complicated, so I'm not going to tell about that. But here, so Alice has so this is, I'm talking about the X quadrature. This is also true for P quadrature. So Alice has X quadrature value. They're distributed like a Gaussian shape on this axis. Bob receives the quadrature values with the noise, but Bob has to renormalize that to match with what has been sent by Alice, and they have to assign a digital binary strings to this analog data by this mapping. So whenever there is a coherent state at this some particular value, they can convert that immediately into a binary value. So then they have a binary string of data, then they have to correct the data because it's a noisy systems, and then whenever you Bob received the noisy version of Alice and then convert the noisy version of Alice bit string, then you have to correct. So you have to do some error correction on it. Then you can do then in the end you can remove, once you know how much information has been leaked to you, you have to remove it, and it's called a privacy amplification. So it involves, the CVQKD systems involves these things like Alice send the quadrature information on amplitude and phase modulator lights. To Bob receives the attenuated version of this light and the measure of the quadrature, and then Bob, because of Bob's measurement, he adds noises there, like noise rates. So the quadrature measured by Bob includes the noise from eavesdropper, noise from electron noise, and also the fundamental vacuum noise. But it works like this. So they have to agree on, so remember, Bob has to measure the quadrature X or P randomly. So they have to agree on, okay, which quadrature they have to keep. So this is called a sifting. Then, as I said, Alice sent a signal with a local oscillator reference. They pass through the channel and they don't keep the same reference. Their phase is going to change. So they have to correct this phase. So there is some procedure called phase correction, and it involves some pattern recognition or some kind of DSP. Then they have to estimate the correlation. Then I'm not discussing further more into that. Then they have to estimate the channel transmittance. Based on the channel transmittance, they estimate the excess noise. And if the noise is below the threshold for generating key, they proceed to make this mapping and the correction and price amplification. If the noise is above the threshold, for each transmission distance, you can identify there is a threshold for the noise. If the noise is above the threshold, they abort the transmission. So once you have the key, you can do this one. Yeah. So you can pass this key generated from the quantum key distribution system to your encryptor. The encryptor takes the key and encrypts it, and then decryptor have the same key, and so you can decrypt it. And since Eve doesn't have any information about this key, it's quite safe. It's not quite, I should say it is theoretically safe against eavesdropping. One thing to mention about CVQK is this direct reconciliation. So Alice sends the data to Bob, information to Bob. Bob receives the noise information. So Bob has to remove the noise from the received data, which is called a direct reconciliation. So Bob has to correct his data to match with that of Alice. This is called a direct reconciliation, and doesn't make the CVQK to go more than 3 dB of transmission distance, which is about 15 kilometers, because Eve can hide inside the channel loss and then get more light to Eve's measurement system, because Eve is always looking at Alice, what she is sending to Bob. Eve doesn't have to worry about what Bob is receiving. But in reverse reconciliation, Alice is going to change her transmitted data to match with the noisy version of Bob. Now Eve has to look into Bob, and Eve doesn't know what is happening inside Bob's detection systems. So this gives a more transmission distance for CVQK. Recently it has been demonstrated for 30 dB of transmission distance, which is around 200 kilometers of fiber, special fiber. And also this allows us to demonstrate the CVQK from satellites or pseudo satellites to ground stations. So one important thing about the CVQK system is its detection. So how you will ask, okay, I know how to detect a single photon is by using a single photon detector. You send the light photon to a detector, you get a click, that's it. But how do you detect the quadrature in CVQK? How do you have the sensitivity enough to measure your vacuum noise? So you have the Holmdel detector. The Holmdel detector, it is a beam splitter, a 50-50 beam splitter. So you send the signal, which we can represent as the complex. Let's say here it's a complex number, which is x is the x quadrature, or p is the p quadrature. And the local oscillator, which is very bright, so it's not really quantum. It is, you can see that's a classical. So you mix it. You interfere with them on a beam splitter. The output of the beam splitter is minus, plus is a plus port, and minus is the other port. Then you have the normal interference equation, right? Then photodiodes, these are the field, electromagnetic field. Then photodiodes, they cannot detect the field, they can detect only the intensity, so you need to square the field. So the photocurrent from each of the photodiode, you need to subtract it. The difference of this photocurrent gives you the quadrature. So if the phase of the local oscillator with respect to the signal, remember this is not photons, you have to think about in terms of the field. The phase of the local oscillator is, if it is 90 degree, 0 degree with respect to the input signal light, that you can measure, you get the difference of this current is, it gives you the x quadrature value. And if the phase is 90 degree, it gives you a p quadrature. Right? Because it's an interference of different lights on a beam splitter, the local oscillator only picks up photons or fields that is in coherence with the local oscillator. One of the selling point of CVQK is this. Imagine you have to do the single photon detection in a lab or in a field or in a bright light conditions. You cannot do it. You need to switch off the lights. You need to blank out your screens. Or in free space communication, you need to wait for the night to do the transmission from satellite to ground. But for CVQK, we have a filtering process that happens here. The local oscillator only picks up the photon that is incoherent with the local oscillator, and it rejects all of the photons. You can do the CVQK in a daylight condition. So in lab, you don't need to switch off the lights. In the field, you don't need to wait for the night to reduce the background light from sun. So that these are the main selling point of CQKD. So we need to make this Hamilton detector short vacuum noise sensitive. How you do it? Right now you say there's nothing to talk about here about that vacuum noise. How you have enough sensitivity to measure the vacuum noise or the photon signal at a quantum level. So this is a Hamilton detector, but it's not enough. You need to amplify the difference in current. The quadrature value is very feeble, comes out of the difference in photocurrents. You need to amplify it with an amplifier, which is electrical amplifier, right? The op-amps. So you have a gain. Op-amps give you gain. So gain times this loss letter field value and the quadrature value, and also you add electronic noise. So all the amplifier is really noisy, so it's very tricky to do this work, because you have now two terms. One is electronic noise, and one is the gain times the quadrature values multiplied by the field of the loss letter. To make it sensitive to the quantum noise or vacuum noise or the quantum signal, you can increase the loss letter power such that the electronic noise contribution is very low compared to the first part of this term. So here you see that in oscilloscope, SUMID. So I'm sending a pulse to loss letter and pulse the signal, the interferer and the beam splitter. And then what you see here is actually the signal. The signal strength is few photons, less than a photon, and then the flat line is they are the electronic noise. So by increasing the loss letter power, you can push your detector to sensitive to the quantum signal, and this is now called a short limiter detection, because your electronic noise is very, very low compared to your short noise or vacuum noise. Once you have the sensitivity to vacuum noise, then you can detect 1 photon, 2 photons. The concept is not detecting the photon, the concept is actually detecting the field. So the ideal performance of the short of the detector is like this. So you have electronic noise, and then you need to test your detector against a different loss letter power and find the loss letter power that makes your detector short noise limited. And also it should make your detector linear, because all the theoretical development we develop based on a condition that the system is Gaussian. The transmitter is Gaussian, the channel is Gaussian, the detection must be then also Gaussian. Or linear in one sense, Gaussian linearity. You need to keep the Gaussian linearity also in your detection. So that is how you detect quantum coherent state. But the quantum state, you can also use it for something different. As I said before, because they show some uncertainty, you cannot transmit a meaningful data on it. You cannot precisely measure it, but we have done something interesting, that we transmit a quantum and classical data on a single pulse. How you did that? Okay, so this is the Gaussian modulator signal, the best protocol in the field. So we generate the signals, and then we displace them into different position in the phase space. Now they are distinguishable. The quantum parts among themselves, they cannot distinguish from each other, but when they displace a group of them into two different locations, then you can assign a classical data on it. So you can say, okay, one is going under, it is bit 1, and one is going to the other side is bit 0. You can make a different constellation of classical data with the displacement. You have heard about the displacement operation quantum optics class. How you do this? It's quite simple to realize a displacement operation. Take a beam splitter, which is highly reflective, and you want to displace a coherent state alpha, then you need a strong pump beta, then mix it. The output is displaced coherent state. If the input is vacuum, the alpha is vacuum, then its output is displaced. The output is just a coherent state, because the coherent state itself defined as a displaced vacuum. So you can do the displacement in a lab. In the quantum mechanical operator, whatever you see in the textbook, you can do that in a lab. So we have made this displacement generator in a fiber, because in a fiber it's easy to handle. And this is an interferometer called the Sagnac interferometer, which is quite stable. So we generate this displaced current state, and then we perform this experiment with this. This is a complete CDQ, kind of a CDQ system. And there you go. So we have received a lot of data, as I said before in one slide, that we have a phase, we need to do some phase correction. When you send a data current state on a channel, it changes its phase. So in the end, you detect it's like a circle. So you have to do some DSP, digital signal processing, after receiving this data to bring back your classical data or the quantum data back to the constellation. Now you see the different constellation that we have tested. And by knowing the amount of displacement, you can remove the displacement and then you bring back the quantum data. So you can, so on a single pulse or single transmission, you can transmit the quantum and classical data on a QKD signal. So that's one interesting feature other than the QKD, and also there are a few others, but I think it's time to wind up here, and that's all from me. Thank you.
Thank you, Rupesh, for this illuminating discussion. So now the session is open to questions. So you can come forward and unmute your microphone or video to air your questions. Also, the YouTube participants can type your questions in the live chat, such that will be answered from here.
Don't worry, it's actually many of the people they have told me that my voice has some ability to make people sleep. So it's not your problem, because I have some cryptic word I feed into your mind so you can sleep while I talk. So that's not your problem. But if you have some doubts, you can also email me.
Can you explain that quadrature concept once again? Yes. Quadrature.
Yeah. Okay. Let me show the screen. Quadrature. That one. The quadrature. Yeah, the quadrature is. So it's simple to understand. So you have so when you draw the graph, you can have a Cartesian coordinates, which is x, y, or polar coordinates, which is r and theta, amplitude and phase. So the light is just amplitude and phase. It's a wave, right? So you can change the amplitude, and then you can also change the phase of the light with respect to another signal, because you cannot measure the phase without a reference signal. You can measure the amplitude without any reference signal, because you can just you can put a photodiode there, and the light gives you different intensity on the photodiode, so that is amplitude information. But phase is relative to something, so you need a local outlet, reference signal, and then you mix your light with a reference signal, and then you say, oh, your phase is some value with respect to reference signal, but the output of this measurement is not amplitude and phase. It's a combination of amplitude and phase. It's like it's just a trigonometry idea. So you have amplitude and phase. The x value is r cos theta, and the y value is r sin theta. Exactly like the p is actually the projection. So I would say it's a projection, but it's actually measuring a signal with respect to a different axis, and the axis is a reference signal axis. So that's why I call this a quadrature, because there is no other way to measure amplitude and phase altogether. So you have to measure quadrature that gives you R cos theta, R is the amplitude, theta is the phase, and you also need to measure the leakage, photons leaking from different channels to the quantum channel that can go to a mask it. So compared to the DVQKD, CVQKD has higher noise tolerance, which makes it a suitable candidate for free space communication, satellite ground stations, or highly dense fiber. But the problem is the CVQKD has a bigger bottleneck of digital signal processing or error correction, which needs highly complex computational power. And DVQKD is much simpler. So DVQKD can go longer distance if there is not much noise from the other background, other channels. But CVQKD can go to some distance. For example, the recent demonstration of CV is 200 kilometers in fiber, and the DV is 500. So there is a difference. So CV works better at a small distance than DV. But CV has higher noise tolerance than DV. And the question is, do you really need to send the light to that long distance in fiber? For example, every city, diameter of a city is 60 kilometer in average. So in 60 kilometer, if you distribute the optical network, those kind of transmission distance, the CVQKD is better in generating keys and distributing keys. But for longer distance, DVQKD is the promising candidate, especially for the satellite to ground communication, but only at night. For the daytime operation, you need a CV. So there are advantages and disadvantages, but comparing to the realistic demonstrations around the clock, DV has much promising feature. And also, for DVQKD, you need to cool the detector to minus 70 degrees Celsius, so minus 20 degrees Celsius. For CV, you don't need to cool it. So in the practical demonstration, if you take a DVQKD system, put that in a telephone exchange, then put that in an aircraft, then you need to match the temperature conditions, so your system can break soon. For CV, it works in room temperature, it is very compact, and it's very low cost. DVQKD detector, one is cost 20K, which is 20 lakhs, I think, in Indian money. 20K, yeah, but for CVQKD, you can make one detector with 1 lakh Indian money. So there is a cost difference. The only problem with the CV is it's difficult. You need to do all this error correction and processing in the computer. So a software skill is essential to demonstrate CV. And for DV, you don't need that kind of expertise in all the things, but that's why you don't see much interest from DV side in the past. But now we have more interest in the CVQKD. Sorry, I was talking about the DV side. So the difficulty to implement it, that makes people to pursue it, because there is an easy option, but there is a trade-off between that. That's all.
Okay, we have one more question. No, two more questions, I think. Okay, one question is from Prime Prabhakar. How does the noise in quantum encrypted communication network compare to conventional optical fiber communication?
In a conventional optical communication, you don't have you have a noise called a bell. You detect it as a bit error rate, which directly proportional to your amplitude of the signal or sensitivity of the detector. So as a number, possibly he knew this number. So the detector, which has sensitivity of minus 30 dB, it's enough to do the classical communication. But single photon detector, the sensitivity is around the single photon level, which is around minus 120 dB. So any noise, you just need a single photon from any other channel, because if in a classical communication, you can leak one light into another fiber, or one light in one wavelength channel into another channel, one photon, and this photon can go to the single photon detector and then kill everything. I mean, make in compared to classical communication system, the quantum communication system is very vulnerable to noise, so you need to protect it. That's why most of the demonstrations, we don't use a fiber with many classical data. We use something called a dark fiber, just for the quantum data transmission. But that's not the case, because imagine if you want to build a quantum network around the world, you cannot make the new fiber systems. You have to use existing fiber system. So the quantum network is really vulnerable to noise, and you need to protect it.
So, one more question from Prime is that, can you please comment on the special fibers being used?
The special fibers. Okay, right now, most of the fiber in the world is called a single mode fiber, which is single mode 28. That's the mode 28 fiber, which has an attenuation of 0.2 dB per kilometer. The special fiber is from Corning, and they have ultra low loss fiber, which has attenuation less than 0.17 dB. So it's some kind of increment in the loss, but I'm not sure that it's going to be. It is available to buy. It's very costly, but it's not. Maybe in future. But what is the need for replacing the current fiber with the ultra loss fiber until it pays you that much of efficiency in your communication? So okay, so that is ultra loss fiber. It's from Corning. Corning is a company that makes the fiber.
So Prime is there. Prime. Are you satisfied with the answer? Prime, I think you can come forward, you can discuss if you want. Okay. Yes. Okay, we have also a couple of questions, but since our time limit exceeded,
there's one.
Please,
I can give one more thing. George Matthew, do we need entangled photons of quantum communication? Not necessarily, but entangled gives you, it's a holy grail. So it's just like you can make quantum communication with the entangled photons, but you need entanglement to sense in future, which is to make a quantum network. Quantum network doesn't mean that only do the quantum key distribution. It can do. It can transmit entangled state, that we can use it for the entangled state for distributed quantum computation, sensing, and other things. But not necessarily you need entanglement. But if you have entanglement, then you can avoid a problem called a trusted relay problem, because to communicate. Imagine you have a satellite that has to deliver key to a ground station A in London and ground station B in Mumbai. So if you have an entanglement, then you don't need to trust the satellite. So you can avoid this kind of a trusting problem if you use entanglement, but you have some disadvantage, and it's really not practical at this moment, except the Chinese has done some work, but it's not that a kind of a commercially viable option. Who is going to do this? Yeah, companies, commercial companies has to do the QKD things in the end. But if there is no benefit from this money that they have spent to build the systems, and then there is a problem. But who knows in future? It can happen. Okay.
Okay, time being, let's stop the question answer session here, because we'll answer all the questions later. Okay, Rubesh. Okay, yeah. I will send all the questions. I think 4 or 5 questions are here. So the time being, okay, we will move to the next session. Okay, all the questions are answered later. Okay, now I welcome Ashwini to propose the vote of thanks.
Good evening, all. It's my privilege to have been asked to propose a vote of thanks. So on behalf of the entire physics department of Government College Karyavatam, I extend a very hearty vote of thanks to Dr. Rupesh Kumar sir for his lecture in quantum cryptography and for his time. Thank you, sir.
Okay, thank you.
Then I would
Okay,
like to
Rupesh.
thank all the participants who have participated for their support and participation. Thank you all. Thank you.
Okay. Thank you, Rupesh, once again for your illuminating discussion. So next session.
It's my pleasure. Thanks. Bye.
Okay. So next session, I'm going to introduce the resource person, Dr. Ram Surat. Dr. Ram Surat is a chief scientist at Control Technologies, Abu Dhabi, UAE. He obtained his PhD from University of Hyderabad. And he's having more than 12 years of research experience in quantum cryptography, especially aspects of this cryptography, quantum cryptography. He has experience from Indian Institute of Science, Kolkata, Indian Institute of Statistical Science, Kolkata, IIT Delhi, i5 Technologies, Abu Dhabi. Today, he will discuss about quantum random bit generator. So, I welcome Dr. Ram Surat to handle the second session on quantum random bit generator.
Hello.
Hello, sir.
Hello,
Yeah,
Sanjeev, can you hear me?
audible. Okay, you can proceed, please. You can proceed.
So, can you see my this presentation? Hello. Hello, Sanjeev.
Everything fine. It's okay. We can see your presentation and also your. Okay, please.
Okay. Thanks, Dr. Sanjeev, for nice introduction. And I really thanks to the organizer team, especially this Department of Physics, Government College, Kariwattam, for organizing such a beautiful webinar. So, in this first session, we have seen that Dr. Rupesh Kumar already talked a lot about quantum communication and is towards quantum technology. He talked about encryption, decryption, quantum computing, error correction, homodynamic measurement, and actually my talk is based on vacuum fluctuation, which is also he already gave one some kind of flavor towards that. So coming to my presentation, first let me just introduce about ourselves, who we are actually. So here you can see that there's a two logo. One is i5 technology and another one is quantum technologies. So this i5 is basically working towards different domain range from like healthcare, finance, fashion, gaming, artificial intelligence, etc. For more information, please visit technologies. This is actually initiated by i5 technology. So here we are working on the quantum information and security. Actually, we are the first in Middle East private-owned quantum lab and developing products from for this like banking, telecommunication, cyber security, defense, etc. So, moving on to my presentation here. So, this outline of talk is I have arranged this like this. Like first, I will talk about this. What is random number and why we need random number and how to generate random number and what are the market analysis right now available for this quantum random number, and then how many types of random numbers there. I'll talk about the pseudo random, true random number, and true random number. There's a different way actually to generate this random number. But I'm since my title of talk is quantum random bit generation, so I'm going to focus more on this portion where I'm going to talk about experimental scheme, theoretical proof of concept, experimental observation, and post-processing, application, limitation of physical random number generator, and conclusion. So to begin with this, the first question comes in our mind that what is random number? So since Dr. Sajju told me that this presentation is just basic understanding, so I have in my presentation coming out and incidents, you know what is the outcome. I mean, it's hard to predict. It's in our sometimes you need to make some decisions like decision. I hope this in audience know many people are aware of a pseudo game. Ludo game. Ludo game is actually we used to play this dice. So a dice gives a random sequence between 1 to 6. So have you thought about where this random sequence comes? So in our mobile, what we are playing this Ludo game, in that actually that random number is based on pseudo random number. It's based on software based random number. For example, and it's a deterministic process that is based on algorithm and it's predictable. Let's say, for example, we can design one, here I'm giving one example of algorithm, like x n plus 1, ax n plus b mod n. So here in this algorithm, we can fix any value x0, a, b, and m, and then we start playing this based on our requirement. Like if we want to generate random number between 0 to 50, so here if we fix some number like x0 is 2, a is 1, b is 2, x0 is 2, and m is like 10. So if we keep changing this value, then we will keep getting like 0 at n equal to 0, we are getting random number 2. Like similar way, at 1, we are getting random number, some sequence like 3, like that. So this kind of random number actually we can predict if we know this algorithm. So for security purpose, this is not very useful. Then there is different types of random number which is based on hardware. So in hardware also there are two different types of random number. One is deterministic, which comes from classical process, and entropy source is not consistent. So since entropy source is not consistent, so what is happening, this one after some time they start repeating their path. And for more information, you can see our paper which is published in Pimana and Nano System. And in non-deterministic case, that random number comes from elementary quantum optics process, which is probabilistic in nature. And there is several ways to generate quantum optics process random number, like optical path generator, time of arrival generator, photon counting generator, attenuated pulse generator, generator based on vacuum quadrature, generator based on the phase fluctuation, generator based on amplified spontaneous emission. So here you can see that 5 and 6 I put it in bold because these two different types of generator we have generated in our lab here. So I'm going to talk about generator based on vacuum quadrature. So to begin with this, I'll just tell you the market analysis. So, I mean, how this quantum technology is growing over time in low. So see, this for this quantum technology, quantum communication, the first part is quantum random. We are here actually, and slowly we have to work towards quantum technology and come up with several products actually. And for more information, you can look at this source, the quantum age technological opportunity. And nowadays, in market, this commercial product available. One of the very old company is building devices for quantum communication, is ID QuantiQ, and then microphoton devices, PicoQuant, QRV 121, QuantiSense Lab, Q-Tools, Delaware, Hexen, Northvolt, and there is some online server that provides its random sequence. You can check quantum random number on demand, University of Geneva. Then there's an Australian National University. There also you can check their website. There you can find this random sequence. So this ID QuantiQ actually they have they already built this QRNG product, quantum random number generator product. So this module is based on PCI interface, and here this speed is 4 Mbps. So if you use 4 module in one board, then it becomes 16 Mbps. And recently, this ID QuantiQ, they have introduced this new device, QRNG device, which is 40 Mbps. And after putting the 6 module in one base, then it's become 240 Mbps. So these are the QRNG stuff available right now in market. And there's some other company called PicoQuant. They are selling this random number based on photon arrival times, and bit rate is actually 150 Mbps, and that is USB interface. The microphoton devices is they are claiming that 16, 32, 64, 128, and 200 Mbps depending on the device grade. Now, I mean, maybe you might have heard some news recently. I think in May, the Samsung with this Samsung launched a mobile A71 5G boost. That is actually based on quantum technology, chip based for advanced security. So these three companies, South Korean technology and ID QuantiQ and Samsung, they have launched this mobile Samsung Galaxy A71, which working principle is this: they are using the LED and the CMOS detector is there, and up to this post processing, or we can call it post processing, they are getting a random number data. So here, coming to our work, and is how we get this quantum random number. So we have defined in some small module. First one is selection of a scheme, because I have shown in previous slide there is several scheme to generate quantum random number. So here first part is to select a scheme and then perform this experiment. So after performing experiment, whatever raw data is there, that raw data pass through the post processing, and after post processing we get this random sequence. Then this random sequence need to be checked that how much random it is. So after it's called statistical test. So after statistical test, we can see that if it's passed that statistical test, we can use for further use. And here just I would like to say that our first proposed optical QRNG, which is in 1994 by Rarity Group, was quantum random generation and key sharing. Here, for more precise and more clear understanding, quantum random bit generator based on vacuum quadrature. So here we have decided in some sub-module. First is that state preparation. In state preparation, we will try to understand that what is quantum in our scheme. Then we measure that one, and after measurement, we get this raw data. this raw data pass through this extractor, and after extractor will get this random sequence that will need to check this statistical test. So here we are using this is our scheme. So in this scheme we are using a very coherent source, highly coherent source. This is laser, and this laser light pass through this optical devices. Here this device is called polarizing beam splitter, and before that there is a lambda by 2. So we are using this lambda by 2 to balance the output intensity of these two ports. So here we are balancing, that's why based on that we add this signal, subtract this signal, and from there we look at this randomness part. So in one port here this highly coherent source is light passing through, and the other port is actually left blind, and we assume that there is something in which is vacuum quadrature. So vacuum is nothing, it's a 0 point energy. So theoretically, I will explain this here about this vacuum. So we consider vacuum state, which is position representation can be written as this form. So if we measure this one, so the magnitude quadrature collapse the wave function into quadrature eigenstate, giving the associated outcome unpredictable as well as follow the Gaussian distribution. So we have theoretically estimated this portion using linear function, and you can see this one. This is perfectly Gaussian, and it's showing a very clear randomness. So for more information, you can check this SPLE and Usually quantum optics. This from press. So here experimental observation is like this. Already I have explained this part. So here you can see that there's a 3 different color. So the signal output of these 2 detector, when we add, so add part is the blue one, it's called local oscillator quadrature, and after subtracting we are getting vacuum quadrature, that is red one, and when there is no signal we put laser off, and it's looking there is no light falling on this detector, that is background count, so that is called actually electronics noise, so L1. So these data bit we have plotted this histogram, and that is showing Gaussian distribution type. So while we are collecting this signal, we need to play with this sampling rate. So here you can see there actually this blue is just behind this red one. So 1 mega sample and 2.5 mega sample, we have collected two set of data, and we plotted this and it's fit this Gaussian distribution. Next, after this, here once we receive this signal, then we pass to this post-processing analysis. In this post-processing, actually there's a two main important thing is that we need to find out this what is the minimum entropy, and next one is the randomness extractor. So next I'm going to talk about this minimum entropy. So what is the minimum entropy actually? So here minimum entropy tells how much randomness from raw numbers can be extracted. For example, let's say we have a sequence of random number 0, 1, 1, 0 like that. So entropy can be defined like h equal to minus epsilon I next to n pi log pi raised to. So here this capital N is actually 2 power n, so small, where this n is analog to digital converted bits. So let's say for example, if we put this ADC with 2 bit and equal to 2 bit, so capital N become 4. So what are the possible outcome for that. So it's 4 means it's 0, 0, 0, 1, 1, 0, 1, 1. If suppose n equal to 1, then possible combination is 0 and 1. Like if n equal to 3, the possible combination is 0, 0, 0, 1, 1, like that. There's 8 possible combination. So let's say, take an example like this one, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0. So since I'm taking here ADC with 2 bit, so we have to look at this, how many pairs are there with 2 bit. So this is 1 pair, second pair, third pair, fourth pair, 5 pair. So in this, in 5 pair, we can see by extending this entropy in this form, P00 for 2 bit, P00, P01 like that. So here we can see that P00 means how many combinations is there of 00. So we can see there's no 00 combination. P01 means how many combinations of 01. So 01 is 1, 2. There's a 2 combinations. So total combination is 5. So 2 by 5. 1 0. P10 is 1, 2, 3. So there's a 3 combinations. So 3 by 5. And P11 is 0 because there is no 1 1 combination. So in that way, if you see this, in that way we can calculate this entropy. So here we calculated entropy is 0.966. So actually, in ideal case, this minimum entropy should be for 2 bit, the maximum is 2. But here we are getting like nearly 1. So if we are looking from entropy itself, we can say that whatever sequence we have, which is perfectly random or is biased towards some 0 or 1. So since this is less, it's like 50%, so it's kind of biased. So I'm just giving one example here. But in our system, what we have used, there we have calculated this entropy for 2 different rates, like 1 megasample and 2.5 megasample. And here at 1 bit ADC, we got 1. I mean, it's more like for 1 bit, it's more random. But 2, actually, ideally, we are supposed to get entropy 2, but we are keep increasing this ADC bit. Okay. Sorry, I'm really sorry for inconvenience. So this minimum entropy, this is actually essential part for this testing this random number. So this minimum entropy tells about how much randomness from that number can be extracted. So for example, we know that minimum entropy or entropy is defined like this: H equal to minus summation Pi log Pi. So in that way, we are going to calculate that whatever we have sequence, like from this random sequence, 1 0 1 0 kind of random sequence. So we calculate this in minimum entropy like this, n equal to 2 power n, where this small n is the ADC bit, analog to digital converter bit. So in that small n is equal to, let's say we are using 2 bit ADC. So in this 2 bit means capital N is become 4. So there is a 4 possible combination: 0 0 0 1 1 0 1 1. If we use n equal to 3, then 2 power 3 is 8. So there is 8 possible combination, like 0 0 0 0 1 0, like there is a combination is there. So I'm giving here one example, which is actually 2-bit ADC. So let's we have a sequence, some random sequence like this. So and we are using 2-bit ADC where the possible combination which we can separate it, like, I mean, we can see a 2 number, like we can check it like this. So in that, how many combinations is there? 1 2 3 4 5. So total is 5 combinations for this random number. And here this H we can write like this, in this form, if we extend for 2-bit ADC. So we look at this P00. P00 means how many 00 combination is there in this sequence. So there is no 00 combination. So P0 is 0. P01 is there's a P01 means 1, 2. There's a 2 combination. So 2 by this total sequence means 5. And P10 is 1, 2, 3. There's a 3 combination, so 3 by 5. And P11, there's no 1, 1 combination, so it's a 0. So entropy can be written like 2 by 5 in this form. So if solve this one, then H equal to 0.966. Here, actually, in ideal case, if there is no biasness, everything is perfect random number, then minimum entropy, the maximum should be 2. But here we are getting like nearly 1. So it means that this random number is not very good to use for security purpose and all. That entropy itself tells about this. So in our case, in our lab, whatever random sequence we have, got it, we check that entropy with 2 different samplings and rate like 1 megasample per second and 2.5 megasample per second. So in that case, like you can see here, this bit ADC bit like 1, 2, 3, and 4. So correspondingly, entropy is keep increasing. Like 2 is ideal case, it should be 2, but we are not getting 2. We are getting like 1.25. At 3, we are getting like 2. At 4, we are getting like 2.75. So here, after this entropy, we check this randomness extractor. So randomness extractor extraction is the essential process required to generate high quality random number that are uncorrelated and uniformly distributed. The central part of randomness extraction is usually an algorithm known as randomness extractor. The randomness extractor receives a statistically weak binary string as input and uniformly distributed random bits at its output. So there is several types of extractor available, but we focus on 2 different extractor. First one is one Newman extractor. One Newman extractor, the raw input bits. Let's say this is raw input bits. So in this raw input bits, wherever 0, 0 and 1, 1 sequence 0, 0 and 1, 1 is available, this be simply discarded. So next 2 bit we can make the sequence 2 bit. So 0, 0 is available here, 0 here, 0 here. So this number we have discarded. We can 0, 0 and 1, 1 discard, and 0, 1 and 1, 0 we keep it. So that is actually extracted output bits. So there is an advantage and disadvantage for this one Newman extractor. Advantage is that this raw input bits is become more secure if you use this method. But disadvantage is that this we lose the bit actually. So it will become shorter if you use this one extractor. Of course, it's become more secure, but we lose the information also. So next is Topless hashing extractor. So in Topless hashing extractor, so first let me talk about hash function. Hash function is a data comparison function from binary string of arbitrary length. We take any length of input, which is actually to the binary string after passing through this hash function, we'll get a fixed length sequence. So here, for example, if we talk about SHA-256 algorithm, and let's input is Cointreau. So Cointreau means if you pass using this SHA-256 algorithm, after passing through this hash function, so we'll get a fix this value is this for Cointreau. No matter whether you are using even single character, A or B or C, any character, you will get this kind of sequence. It's a fixed length. For next example is that Cointreau is quantum optics based R&D company. So that hash value or digest value is, you are going to get a fixed length. So how it works actually? So here, this Topless hashing extractor, this is a Topless hashing matrix, and this is our raw data. But we got it from our, like QRNG, and after passing through this, whatever sequence is getting, this is extracted raw sequence. So next part is this autocorrelation. So we have a sequence, this random sequence. So in that we are looking at self-correlation or field correlation. In that case, you can see here that this autocorrelation is for raw data bits. So in raw data, autocorrelation is 10 power minus 2. And after passing through this Topli's Hessian structure, we are getting like 10 power minus 4. So this one is more towards 0 compared to this. For raw data bit is 10 power minus 2. For after passing through this Topli's Hessian, this one is more towards 0. Means this is more uncorrelated data, random sequence, you can see. So after autocorrelation, we have calculated bit rate, means what is the speed of our generation rate. So in that case, bit rate is defined as sampling before post-processing. We define sampling rate into ADC bit, and after post-processing, bit rate is defined sampling rate into entropy. So here you can see this bit rate we have calculated based on the ADC value. For one, it's like this. May keep increasing this ADC point, so we are going up to here maximum bit rate. So after calculating this speed and all, we also check that whatever random number we have, whether it's passed the statistical test or not. So although testing the random number is a non-trivial task, and research on this subject is under continuous progress, however, it is possible to determine the likelihood of a sequence being random. This can be achieved through a well-organized set of various statistical suite available for testing randomness. For example, NIST, DIHARD, and there is some other tests also. These tests provide the statistical properties of number sequence and compare them to the expected value of true random number sequence. We have used famous statistical test suite from NIST, National Institute of Standard and Technology, to evaluate the performance of our proposed prototype QRNG. Here I'm going to talk about how this random net this NIST test work. So actually that is this NIST test is based on p-value, which in case this must be lie between 0.01 to 0.99 to pass the test. So here we are using this Ubuntu software for that. So this test is actually source for Ubuntu. So here these are the command we use, like we update GCC and GCC. These are the command where we test, and then finally we took this post-process data and pass through this random. It will generate another file where there are 15 different types of tests is available, and we can check that value. So here in our case, we tested, and this is the threshold value. So you can see there's all the 15 tests, like frequency, block frequency, cumulative, run, long run, rank, FFT. This is 15 different types of tests there. So all are passed in our case. And this, we have taken actually 1.25 megabit to test this random number. So there's a lot of application of this quantum random number generation, like quantum cryptography, online and mobile authentication code, CAPTCHA, digital signature, cryptography algorithm and protocol, scientific modeling and simulation, seed of encryption key, data center, cloud environment, smart network, artificial intelligence, security application, hardware security modelers, entropy generation for data center, VPN encryption, password, PIN number generation, gaming. There is a limitation for hardware-based random number actually. So limitation is like if the system is sampled at high rate, there is not enough time for the system to change, and random number are not independent. Means random number will be dependent in that case if we increase the sampling rate high. And it is difficult to give a convincing argument for randomness of data in that case. Adding any external devices usually inconvenient and there's a large chances is fail or difficult to detect official, I mean, failure or difficult to detect. Official recommendations suggest introducing a startup test, a total failure test, and online test to check error during operation. So finally, I would like to conclude. So here is that we have hereby experimentally and theoretically investigated a non-deterministic quantum random number generator based on measuring the vacuum quadrature. We have asked a fast randomness extraction scheme based on Topless algorithm for processing the output digitized signal. Our scheme gives a true random bit stream which passes standard test suite. The final generation rate is 1.4 Mbps, and which is limited due to bandwidth of the detector. So this is what our lab actually. You can see here there's a curtain. So when we used to perform our experiment, we used to switch off all the light, and we used to avoid background light also. Thank you.
Thank you, Rubesh. So thank you, Surat, for presentation. And now the session is open to questions. You can ask questions directly from the group here, or you can also, watching YouTube group, you can type YouTube live chat your questions. Amal Srijit is asking question: does our silicon-based processors are fast enough to process quantum computing?
Actually, this quantum computing is a different part, and I'm talking about here quantum random number generation. So, of course, based on a requirement, I think we can make a convincing things. Once here, does our silicon-based processor are fast enough to process quantum computing? Actually, there are two different questions: silicon-based processor and the quantum computing. I'll check this one. Right now, I can't say this.
On another question from Nishant.
Yeah. Nishant, okay. So
Yeah.
there's 15 criteria by list, quantify QRNG as pseudo random number.
Yeah.
So, already I have mentioned because in this talk that this is like test is a non-trivial thing. So research are going on. So right now I must say that yes, because most of the people who is working towards quantum random number generator, they are convincing with this new test. So currently I would say yes. Okay.
Yeah, one more question is there. Govind S. How does the QRNG depend on devices connected?
How does the QRNG depend on devices
connected?
QRNG depend on devices connected, because I'm just the question is not very clear to me.
Yeah,
can you just
Govind, you can come. I think Govind is in this group. Govind, you can come forward and ask directly. You can interact directly. Govind, please switch on your mic.
Okay. I think if I'm clear about what he wanted to know.
Okay.
I have mentioned that due to device limitation, our generation rate is like Mbps. Of course, it's depend on devices. Like QRNG is actually this is depend on bandwidth of the detector. So if our bandwidth is high, then we can go for higher, sampling rate, and then speed is depend on sampling rate. So of course, in that way, we can connect this thing. So of course, this depend on device bandwidth, and it's I'm talking about detector part. I think we can have more discussion about that. Or you can just again type here. You can write to me directly on my mail. For more discussion.
Okay. Is there any other questions?
Anyone can just send message to directly message me on this mail, and definitely I'll try to explain it.
Okay. If there is no other questions, okay, let's invite Anandu to propose the vote of thanks.
Hello, good evening to all. I deem it a great honor and privilege to propose the vote of thanks on this auspicious occasion. First and foremost, I thank Dr. Ram Sursar for his valuable lecture and time on behalf of entire Physics Department of Government College Karyavattam. I also wish to express my gratitude to Dr. Sachivde and all the faculty of Department of Physics, Government College Karyavattam for organizing this webinar. Also, I would like to thank all of the participants for their active participation in this webinar, and I apologize for the poor network connection that occurred between webinar. Once again, I thank you all for your attention. Thank you.
Okay, thank you. Thank you once again, Surat, for your illuminating discussion on this quantum random number generator. And thank you all for participating in this seminar. And we will give you the feedback link. Please remember to fill the form. We will distribute it via your WhatsApp link.